Okay, so uh, let us discuss the following thing. So we saw a lot of examples of equations that had partial derivatives up to 2 in some variables, and coefficients in these equations were constant. Like, all these effects are quite natural because if this equation is more or less fundamental, then it should not be of very high order, and it should also be coordinate independent, because we know that our space is homogeneous. So of course other examples can appear. For example, if we take some nonlinear equation, take some solution of this nonlinear equation, and then obtain some linear equation at the background of this solution. But it is something of high level. In principle, we will think also about such equations, but the basic example is the ODE with up to 2 derivatives and with constant coefficients. And also the linear ODE, because if it is nonlinear, usually it requires some non-trivial methods to solve, and they are specific for different equations. So it contains some much richer science. So the problem we want to solve is the following. So we'll start from the equation of this form: aij du over dx I. Well, should they care about? Well, let us just write. No, let us take care about upper and lower indices for some time. Dxi, dxj. So it's a combination of all possible second derivatives. Ij from 1 to some n, plus the first derivatives, bi du over dxi, plus probably some constant times u. And when we ask about some classification, we need to say classification with respect to what, the transformations which we want to apply to this equation are the following. We can perform some change of coordinates. Namely, since these coefficients are constant, so let us write that they are constant. We don't want to break everything, and so we use only the linear changes of coordinates. Namely, we choose some x, how, how to denote them? Let us denote them x tilde j equal to some matrix A j k x k. And another transformation which we can use at some moment is a multiplication of u by some function. And again, since we don't want to break this constant coefficients, this function should be linear. So it should be some di xi. And that's all, basically. The question is, what is the effect of such transformations? So we see that this equation can be written as some quadratic form of this dx is acting on u. So we can write this equation like sum of a ij di dj plus some bi di plus c acting on u is 0. And the subject written here is called is a symbol of this differential operator. People also turn it to some function of some letters p instead of this d's, and write something like aij pi pj plus sum of bi pi plus c. This is some function f of p. This is code symbol. And you can write these functions for all these equations. And if you put the constant levels or zero levels of these functions, you will see some spheres, hyperboloids, paraboloids, and this classification. So it's some suggestion that this classification of equation is more or less the same as classification of surfaces in the and of quadratic surfaces in the n-dimensional space. So, and we will basically do this. So, but let us now see this analogy of this classification of surfaces. Namely, let us see why all these transformations act just some linear transformations of these differential operators. So we have so on one side we have di's which are d over dxi's, and we have a relation that di of xj equals to delta ij. And on the other side, we have some x tildes. So x tilde j equals, well, it is written over what is an x tilde. And we want to find corresponding derivatives in x tildes, which would also act in the same way. So we want x tildes d tildes I such that d tilde I x tilde j equals to delta ij. And it's a kind of obvious suggestion to look for such operators in the same form, to find them as some linear combinations of DIs. Let us say that d I tilde equals to some combination of b I L and act with this operator on x tilde j. So it is this sum of L, B, I, L, D, L acting on sum of K. By the way, if I don't write sum and some expression contains repeating indices upper and lower, it means that there is a sum over these indices, so-called Einstein notation. But here I just forgot to write the sum. So if you now act with the separators here, I just have delta Kronecker. So sum over LK, BI L, A K J, delta K L. So K should be put equal to L, and get sum over L only, B L I A J L, which means that we have a matrix product of two matrices. Namely, it is a matrix product of AB a component ij. And since it is a derivative of xj tilde, it should equal to delta ij. So components of this matrix are the same as components of the unit matrix, which means that the product of these two matrices A and B is 1. N times B So it means that if coordinates are transformed by some matrix A, derivatives in these coordinates are transformed with the inverse matrix. Now we have arbitrary linear transformations that originally acted on the space of coordinates, but now they act on the space of this derivatives or on the space of Phys. So we have arbitrary linear transformations which act on some space, and we have some quadratic surface in this space. And we know that all this that if we act with this group of transformations, then this quadratic surfaces can be put to one of these canonical forms. And let us just repeat the same arguments for this differential equation. And by the way, there is also another thing. We had two transformations. One was about the linear transformation. Another was about multiplication by some linear exponent. And let us see how the second transformation acts. So. So originally we had this operator. Let us maybe write that we had some function of this PDEs. And this function acted on U, given there. And now we say that this U will equal to U tilde times this. So you don't try to use, right? Okay. So let us substitute it here. And let us write from the beginning in this form. So there is some conjugation of this operator with this exponent. And let us see what happens with a single differential operator if we conjugate it with such object. And what happens if we conjugate with some of dRxi, some operator dk. So to do this, we act on some function f. So when we differentiate it, we need to differentiate first this exponent and then function f. itself. When we differentiate, by the way, who can tell what we will get after this computation? Hmm? Oh, what precisely? So we are trying to understand what happens if uh, we multiply u by some linear exponent. Uh, Originally, you solved some equation with some function of this derivatives in xi and xn, and this new you solve the equation with the differential operator conjugated by this linear exponent. Mm. The question now the question is what happens if you conjugate just a single differential operator d in decay? And to check this, we need to take this conjugated operator and act on some function f. This is a test function to understand how what kind of operator we have now. The question is simply how to differentiate of product of some exponential and some function f. In this one, or what? Ah, it's because it's zero. We can just multiply because it's more convenient. Hmm? Hmm? But what kind of sum? What precisely do we have? Mm-hmm. Mhm. Times something probably, right? Hmm? But we have two exponents. Don't they cancel? Hmm? Hmm? Mm-hmm. 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 Okay, thank you. So it's correct. It's just a product of two functions, and one of these functions is exponential. And now, if you look at this left-hand side and right-hand side, we can conclude that conjugation of this operator of this derivative operator is a decay minus this number. So the consequence is that e to sum of dixi decay e to minus di x xi equals to decay minus decay. So, that's all. So this multiplication by exponential kind of performs this shift on the space of linear differential operators. It shifts them by constants d. So is it clear? And now, if you have if you have some arbitrary function of these operators, if you have, for example, a decay to the power L, for example, if we have decay to the power L, d m to the power p, and we conjugate them with the same exponentials. We can write that it is a decay, it's a conjugate operator to this to power L sum of dixi dm to power p. And we know how to conjugate. So if you open all these brackets, you see that all exponentials except the first one and the last one cancel. So it is on the left-hand side. And on the right-hand side, we can just apply this formula to both of these operators and see that it is decay dk minus dk to the power L d m minus d m to power p. And well, in principle, we can write anything else here. So is it fine? So, and another consequence of all this is that this conjugation of some function of d1 dn. So mm, mm, is just the same function with differential operators shifted by these complex numbers. So it is f of d1 minus d1 and so on, dn minus dn acting on u is 0. So we have at the same time such transformations which perform linear transformations of these derivative operators, and we have such linear shifts. So it is essentially the same set of transformations that are used for classification of quadratic surfaces. So we can shift beginning of coordinates, and we can perform linear transformations. Okay, so are there any questions? Yeah. Okay, now let us go further. So now let us try to use these transformations. So namely, let us first focus on the quadratic part of our operator. So that's kind of the first step. We have this sum of a I j di dj plus something acting on u, and now we do what people usually do with quadratic forms. So, for example, we have some non-zero term with, for example, di some coefficient di squared plus some di times alpha i's some alpha j's dj's. Let us so if this matrix is generic, we can just say that there is some d1 squared with some sign, positive or negative. This C can be different. And there are some terms which are linear in di, and there are some other terms, some beta ij di dj. So from 2 from ij to equal to 2 to infinity. to n, and plus other terms which we don't care about now. So it acts on u and gives 0. So what can we do? We can just say that, well, let us put here plus minus c, thinking that this c is positive. So here we combine the full square, saying that there is plus minus c times d1 minus plus 1 over 2c, and this sum goes from 2 to infinity to n. Square. And now all other terms. So there is this term which we had originally, and there will be another term with the same derivatives that comes from the square of this. So plus 1/4 1 over 4c. So it is a square of something containing d1 and some other operators, and also plus something plus some linear terms. So when we see this, we can just say that let us choose the new coordinate, well, the new derivative to be d tilde 1 equal to square root of c times d1 minus plus 1 over 2 square root of c sum of alpha and j dj from j equals to 2 to n. So we have already put one part of this operator to this canonical form. It is just plus minus d1 squared. Then we proceed further and get d2 tilde equal to some c prime d2 plus some combination of alpha primes dj from j equals to 3 to n, and so on. So it will be some triangular change of derivatives. So it is some triangular matrix. So we can say that d1 tilde and so on, dn tilde equals to something of of this form. And this is what is called Gram-Schmidt procedure. So this way we can, of course, we can have some degenerate cases. We should take care about the order of these operators. But in general, it is clear that we can always do like this and put this quadratic form to a diagonal form with coefficients plus minus 1 and probably 0. Mm. So the result of this transformation is the following: that our equation is written as some number of d's with pluses, d tilde plus d1 plus d, for example, p squared. Then minus some number with minuses. Sorry, d p plus 1, d p plus q squared. And here we have some combination of the first derivatives, which are also transformed somehow, but it will still be a combination of the first derivatives. So here we will have some b tildes I times d d I tilde, and also some c, which is the same as before. So we have this operator acting on U. So are there any questions about this so far? So I basically put a quadratic form to the canonical form, but its quadratic form is not of some variables x or y. It's quadratic form of derivative operators. Not. We just don't care about this because these derivative operators commute. They're derivatives and independent variables. And all other operators are just multiplications by numbers. So is it fine? Okay, so now we have this, and let us do further simplifications. Probably. Well, probably I will erase these equations because at least now You see why all these equations are written without any parameters, because these parameters are absent in the quadratic form. The only invariants under the real changes of coordinates are numbers of pluses and minuses in this form. Okay, so. Okay, now let us try to do something with these bees. Mm. And namely, let us combine full squares also with bees. Mm. So here we have this p pluses, q minuses, and it works like this. We have d1 tilde plus b1 tilde over 2 squared plus and so on plus dp tilde plus p tilde over 2 squared minus dp plus 1 tilde minus bp plus 1 tilde over 2 squared So we have hidden all these b's inside derivatives. But here the problem is the following, that in principle this p plus q can be less than the total number of variables. So in principle we can have another sum d b tilde p plus q plus 1 d tilde p plus q plus 1 plus bn tilde d tilde p plus dn. So we can have these terms which cannot be hidden in the second derivatives. And we also have this term which contains c that was here before, and also squares of these b's which should be subtracted. So it will be c minus 1/4 b1 tilde squared plus b p tilde squared plus 1/4 b p plus q tilde squared p plus 1 p plus q. All this acts on u and gives 0. And this number can be called c tilde. Now we can use another freedom for this variables which don't participate in the quadratic part. We can perform some linear transformation which makes this just another derivative in coordinate p plus q plus 1. So it is some vector in the n minus p plus q dimensional space, and we can rotate it to just the first basis vector in this space. So we can say that this well, let me write it here. We can say that this differential operator in general equals to so this is some epsilon times d with 2 tildes p plus q plus 1. I put here epsilon because it can be either 0 or non-zero, because in principle it can happen that either the number of these variables is 0, or it turns out that coefficient in front of them is 0. So everything is possible. So after this substitution we have and also let us denote such combinations d with 2 tildes. So this will be d1 with 2 tildes. So now our equation looks like d1 with 2 tildes squared plus d p with 2 tildes squared minus d p plus 1 with 2 tildes squared minus dp plus q with 2 tildes squared plus epsilon d p plus q plus 1 with 2 tildes plus c tilde. All this acting on u is 0. And now there are different cases. So one possible case is epsilon equals to 0, c tilde equals to 0. In this case, it is just this equation d1 So depending on the number of pluses and minuses, it gives some Laplace or wave equation. So people usually don't consider equations that have more than one derivative, with opposite sign, because it is something pathological. It's like several time dimensions, and it usually does not appear. So it's either all pluses or all minuses, or all pluses and one minus, or vice versa. So another situation is when we do all these procedures and end up with an equation for which epsilon is for which epsilon is 0 still, but C tilde is non-zero. So it will be the same. But also plus this constant. This is and also we can scale these coordinates to make this constant 1. It does not matter. We can put here 1, we can put here arbitrary constant. Yes. This is a Helmholtz or Klein-Gordon equation, depending on the number of pluses and minuses. And in the third case, when epsilon is non-zero, in the sense when we when we diagonalized this quadratic form, but realized that there is some variable which enters only as the first derivative. So in this case, we have so epsilon is non-zero, and in principle we can have some C tilde which is also non-zero. But in this case we can combine these two terms. You can say that on this epsilon d tilde p plus q plus 1 plus c tilde equals to sum d p plus q plus 1, or maybe minus, with no, let us take put plus with 3 tildes, and then this equation is d1 with 2 tildes plus dp with 2 tildes squared. Like this. So in this case, it is some kind of generalized heat equation. But here actually people don't consider such equations with arbitrary numbers of pluses and minuses, because they are all, I think, pathological. The only equation that people actually study is this one, where the first derivative was with sign plus, and there are some second derivative with minus signs. So we will understand at some moment why why we have this restriction and why other equations of this kind are pathological. So the only good equation is this one, which is the actual heat equation. Okay, so it's the end of classification of such equations, and we see that they don't have any parameters. The answer is that if you take such equation with arbitrary constant coefficients, then it can be put to one of these several forms, and it does not depend on any continuous parameters. And so when we write equations with coefficient 1, we actually consider the arbitrary equation of this form. We only need to study the different types, like this Laplace and wave equations separately, heat equation, and also some of this Helmholtz or Klein-Gordon equations. So, are there any questions? So, I will also give some home problems to put some particular equation to this canonical form, and also to reconstruct the change of variables. Because here, when I was doing all this, I was just writing that, let us say introduce some new differential operator d1 tilde, which is a linear combination of DIs. But we should remember that such transformations correspond to the linear change of coordinates axis. And in principle, we can recover this transformation of axis and say that it is the actual change of coordinate that brings this equation to the canonical form. So, are there any questions about this? Okay, so let us maybe study the first meaningful equation of this kind, namely the wave equation in 1 plus 1, and try to actually solve it. Hmm? Which one is the first? This. So by the way, it's my email on the top. You can write there if you have any questions. Okay, so uh, but I don't have questions because everything's clear, or because something is unclear, but unclear what precisely. Hmm? But who can say that you understand what's going on and what to do with some particular equation if you meet it somewhere? Oh, so the question is, you don't have questions because everything is clear, or because everything is unclear? Ah, okay. So, but maybe the best way to understand if everything is clear is just to try to do all this with some particular equation and write explicitly this change of coordinates which brings it to this form, and maybe also check that it actually works. Okay, so let us go further. So, uh, well, remember this equation had this form. And so it is the canonical form, but it turns out that the best form is not canonical, but something different. Um, and namely, so if you write it as a differential operator, it is dt squared minus dx squared acting on u equals to 0. And the right thing to do here is actually the following: is to factorize this operator, to write that it is dt minus dx times dt plus dx acting on u equals to 0. So, and it suggests us some change of variables. So, why is it nice? Because if you say that these operators are derivatives in some other variables, it will be just some equation that makes derivative in two different variables of u equals to 0, which means that this u is sum of functions depending only on one variable and on another one. And if you want such coordinates, we can write them. So it's easy to check. So let us say that there is xi, which is x, which is t plus x, x, and eta, which is t minus x. They are called right cone coordinates. Mm. So now the question is what is the relation between these operators and these coordinates? And let us write some kind of matrix. So dt minus dx acting on psi, dt minus dx acting on eta, dt plus dx acting on psi, dt plus dx acting on eta. Oh, so who can tell what we get in the right hand side? Hmm? Mhm. Yes, and here. Mhm. No, no, no. Okay. Hmm? Yes. Mm-hmm. Thanks. So this tells us that this derivative can be identified with 2 times d over dt, and this derivative can be identified with 2 times d over dxi. So dt minus dx is 2 d eta, dt plus dx is 2 d psi. So our equation now becomes uh, d psi d eta acting on u equals to 0. And if you want to solve something like this, it's super easy. So let us look at it this way. So derivative in psi of some function of some function is 0, which means that this function is a function uh, of eta only. So d eta u equals some function of mm, eta. Uh, and now, how to solve this equation? This let us say that this function of eta is itself derivative in eta of some other function, because we can just integrate it, and like compute an indefinite integral and say that the definition of this function in big F. Uh, but now the question is, um, we know that derivative of this eta in eta of u minus f of eta equals to 0. It means that this u minus f should be just a function of psi, because otherwise the derivative will be non-zero. Therefore, u of therefore u minus u equals f of eta plus some g of psi. So in principle, it is clear from the very beginning that if we substitute it into the equation, it will be solved, because when we differentiate in eta, we kill one of these functions. When we differentiate in psi, we kill another one. But it is a kind of rigorous proof that it is the general solution. So, and hmm? Some function, like you see that you can substitute any function f and g, and this equation will be satisfied. So any f and g Now there are, of course, various interesting questions, because if we have some combination f of psi plus f of theta plus g of psi, we can substitute anything like step functions, something which is differentiable nowhere, and so on, and formulate the solution of this equation. But if you look at the equation itself, there is some natural suggestion that this function should be at least twice differentiable. But people actually invent some simple ways to overcome such restrictions, and to have this formula as the general formula. So one should not necessarily restrict to to good smooth functions. So we can look at this procedure and the solution as some formal thing. Okay, so are there any questions about this? So in principle, we can kind of solve this equation for but the question is now what precise problem should be formulated for this equation, because it is a general solution, but a general solution with what conditions, like how to convert these functions to some initial value problems, or vice versa. So now let us study this. Hmm? Because just define f of theta as the indefinite integral from some c to eta f of eta prime d eta prime. So is it fine? Hmm? Yes, at some point. So it's basically some indefinite integral, which is defined up to constant, but we don't care about this constant. So any other questions? Okay, so let us try to formulate and solve some initial value problem. So on the real line. So far, I didn't even care about the domain of definition of this U. It was just some function of t and x, leaving no one knows where. But let us formulate it more precisely. So we have U of t and x, and this t, so let us say that t is greater or equal than 0. and x is real. So we don't have any restriction on the real line yet. So we have this function defined for the positive times. We have our equation dt squared minus dx squared u equals to 0. And we can define some initial conditions. So these initial conditions are clear from the physical point of view, because it is because originally this problem described a motion of some string with some tension. So to define its evolution, we need to fix initial shape of the string and also initial velocity of different elements of the string, because it is described by a second Newton law. So the initial velocity matters. And we expect that from the physical argument that it will give us some solution to this equation, and this solution will be unique. And so I'm not proving uniqueness so far, but to prove existence, we will just need to construct this solution, and we will do this now. So the formulation of the problem is the following. So this u is defined for such t's and x's, and when t equals to 0, so u of 0 and x equals to some u0 of x, some function, and u dt of u of t and x when t equals to 0, which can also be denoted as ut of 0 and x. So it means a time derivative. It's another notation. It will equal to some other function u1 of x. So it's a profile of a string itself, and it's a profile of its velocity. So we have these two functions, and we have these two functions in the solution. And the question is, what is the relation between these functions? So it's a formulation of a problem, and now a solution to this problem. So so u of t and x equals to f of I forgot who was eta. It was t minus x. F of t minus x plus g of t plus x. So writing this formula, we already solved the equation. We only need to find these functions from initial conditions. And if we substitute it, we see that so when t equals to 0, f of maybe it was better to write x minus t, but let us maybe change to x minus t, because it does not matter, but it will be more convenient for all computations. Sorry. Or maybe just use f minus and f plus. F minus, and to avoid confusion with that functions. So this first condition says that f minus of x plus f plus of x is u0 of x. The second condition for the time derivative tells us that f plus prime of x minus f minus prime of x equals to u1 of x. So we have these two equations, and we only need to integrate the second one to find the difference between f plus and f minus themselves. Okay, so the second equation tells that f plus of x minus of x equals to integral from some point of y maybe. So if we now combine these two equations, we find that f plus of x equals to 1/2 u0 of x plus integral from c to x. So 1/2. And if we now write the solution, which is the sum of two, so that's one part. Another part is this integral. So here we have difference. So it is integral from x minus t to x plus t u1 of y dy. So and this is a solution to this equation with these initial conditions. So are there any questions about this formula? Which first integral? Yes, thank you. Yes. It's clear that this satisfies the original equation because it's just sum of functions of t plus x and t minus x, and it's also clear that it satisfies these initial conditions. And uh, uh, now we can also draw some pictures for some initial conditions. It's basically the same picture in all these situations. For example, let us ask what happens if u1 is 0 when velocity of the string is 0 and u0 is something. So it's easier just to draw plots of these functions. So, for example, let us consider u0 of this form. Let us say that it is some triangle. For example, of height 1 and width also 1. This is we can write it as some function, but in general, it's enough just to draw a picture. And let us try to find, for example, u of time that equals to 1 1/2 of maybe it's better to say that it and this height equals to 2. No, 1 is fine. So we'll have some picture of the following kind. So what is written here? We should take this initial condition u0 divided by 2 and place 2 copies of it at points x plus t and x minus t, and after that take sum of them. So if we follow this prescription, then we will have something with a maximum at 1/2. So here it will be 1. Here minus 1/2 minus 1. Here is 0. And you should also write this 3/2 and minus 3/2. So there will be this triangle shifted to 1/2 one triangle like this. Another triangle shifted to minus 1/2. Oh, and values this values at the maximum will be 1/2. So it is 1/2. And if you want, if you now want to take some of these two triangles, we see that here derivative is plus 1/2, here is minus 1/2, so it will be some constant function in this domain. And here it will be something of slope 1/2 or minus 1/2. So it will be this picture. So it's a sum of triangles which shifted a little bit. And if we go much further, for example, if you consider this for t equals to 2 of 2x, it will be, and the picture was two independent triangles at different points. X u. So it will be 1, 2, -1, -2. Maybe 2 is too much. No, it's fine. We will have triangle here and triangle here. So they will move independently in the different directions. Yes, of course, for this particular initial condition. But this phenomenon is general, because if you consider something with a finite support, then if 2t is greater than t or 2t, if t is greater than this support, then we have just two independent copies of this initial condition, which travel with the speed 1 in positive and in negative direction. So. And we can also notice the following thing, that when we consider u1 equal to 0, we get a situation where f plus and f minus are the same, like f plus equals to f minus, maybe up to some constant which does not matter. But if you instead consider the situation when u0 is 0 and u1 is something, we will have the inverse situation. We will have this initial profile and inverted initial profile moving in the opposite directions, because it's also clear that if u0 is 0, it means that these two functions should sum to 0, so they have opposite signs. So it was an example it was this example. So when u1 is 0, means that f plus equals to f minus. But if we consider u0 equals to 0, then f plus will equal to minus f minus. And the pictures which appear in this case will have this form. We'll have, for example, such triangle here, and a reversed triangle in the opposite direction. So when they collide at 0, we will get a solution that that has 0 coordinate, but speed, which is invisible, will be non-zero. So if we run this evolution back in time, we will see pictures like picture like this one. So it will be a sum of such functions. Which means that so if you draw a sum, it means that oh, it's in bad picture. Let us make it at least somewhat precise. So let us place one triangle like this, and another triangle like this. So now if we compute their sum, what happens? This corresponds to the situation where one function is 0, another is already non-zero. Then we have a sum of functions with opposite slopes. So it is some constant value. When we go to this point, the slope of one function changes to the opposite, and the overall slope becomes big. this way we go through 0, and at some moment we have another change of slope, then we have again another constant function, and at this point we have another linear function which goes to 0. So this is what we get as a sum of two triangles. So looking at this picture, we can understand what happens. It was some initial condition with positive velocity on the right and negative velocity on the left, and we obtained two such initial displacements which then started to grow and to move to the left and to the right. And at some moment, after some longer time, we have two perturbations moving in opposite direction, having opposite values. But everything started from initial condition with u0 equals to 0. But all this is about some, I don't know, physical intuition, because if you want to write some formula for a solution, you can just take this, and this is everything we can need. So, are there any questions about this? Hmm? So it's the plot of u of some t which equals to something and x. So we have a function of two variables, and the question is how to draw such function. There is of course an option to draw three-dimensional plots, but it's possible in Mathematica, and but not on a paper usually. And it's easier to draw one-dimensional u of x for some fixed t. So it's kind of description of the evolution of a profile of a string with some initial conditions, either this or this, or we can also consider combined initial conditions. So, no. What do you mean by a point in a plane? Oh, so it is x. It is u. A t is a parameter of all these plots. So nu x. It's a plot of function u of t and x with some fixed value of t. Yes, it's for some particular value. So here I was drawing it for 1/2 and for 2, and here it's for some values. We can choose which precise values. Uh, no, for sure you should have intuition, because, but uh, and to get it, you can just take some initial profiles and draw this plots for some small or big values of t. But what precisely is non-obvious? Because here I did literally this. I said that let us consider some initial condition u0 equals to 0. And let us consider f plus of x equal to this step function. So f plus of x is this triangle, and so x, and correspondingly f minus of x is the inverse triangle. Right? So it's clear that we can consider uh, such initial conditions. Right? Now the question is what u0 and u1 correspond to these initial conditions. So we just look at these formulas. So we have chosen this f plus and f minus such that their sum is 0, which means that u0 is 0, right? Mm. And u1 equals to a difference of the derivatives in x. And and if we compute the derivative of such function, so let us draw u1. I think a little bit, and draw a plot for u1. So can you say how it looks like? So there is a formula for u1, it is this one, and there are plots for f plus and f minus. So we can say for definiteness that it is 1, this is 1, and this is -1. And a function in between is linear. So it is 1 minus x here, and here it is 1 plus x. So linear function which goes to these points. So can you say what is the plot for u1 in this case? Yes. So it is discontinuous at 0, but we don't care. Uh, so so here it is 1, here is -1. And we have the steps 2 and -2. So our original velocity was +2 on the right and -2 on the left. And now everything I'm doing is the following. I mean, on this picture, I'm mm, taking this F plus and F minus, shift F plus a little bit to the right, uh, F minus a little bit to the left, and take a sum of two piecewise linear functions. So if one function is 0, we know that it is just another function. So we can draw this element just copying on that other function. On the next interval, we know that it is a sum of two linear functions with opposite derivatives. So derivative of this combination is 0. So it will be some constant. It will be constant until the sign of one derivative changes to the opposite. Then it becomes linear again. And we also understand that this function is odd because it is because if we change x to -x, this point goes to this one. So it goes so 0. Mm. Yes. Thank you. Yes. Well, let me think. U1 was F plus minus F minus. Yes, it's true. Thanks. But then maybe, no, it means that I've drawn, hmm, I missed F plus and F minus on the left. Because this definitely corresponds to this plot for F in this plot for U. So it should be in this combination. Mhm. So, but but generally it makes sense to draw such to draw a few such pictures yourself and understand that you can draw anything else because they are all just sums of some of the differences of some functions shifted by plus and minus d. So, but, hmm? Because no, what's the question? So, hmm? Hmm? So, uh, not in because it is the formula that we have here. U of t and x equals to f plus of t plus x plus f minus of x minus t. So if we have some no, let us draw it here. Huh? Mhm. So the only question is who goes in which direction. So we need to check what value of x corresponds uh, to 0 to x minus t equals to 0. So we see that it is the value of t. So f minus goes to the right, and f plus goes to the left. So this vanishes when x equals to t, and this vanishes when equals x equals to minus t. And this is precisely what is drawn here. So f plus goes to the left, f minus goes to the right. So, so maybe that's all for today. Uh, and tomorrow we meet again at 2 because advanced geometry has not started yet. And starting from the next week, I think you'll have first advanced geometry and then advanced mathematical physics. Also, I forgot to say something about the exam. So the only thing you need to know, or maybe the almost the only thing you need to know is to solve problems, and mainly to solve the equations with some initial or boundary conditions, and also to be able to put them to a canonical form to do such things. Um, so um, uh, this will be sufficient to pass it. And I will also give some problems during the semester, which is better to solve to understand that you understand what's going on, and also similar problems will be at the exam. So, uh, so I will not ask some complicated questions about proving of some existence and uniqueness about restrictions on the classes of functions, unless it is something really essential for a particular problem. Like sometimes it happens that differentiability of one function defines the asymptotic behavior of another one, and in this case it will be important. And Uh, so it was written somewhere in syllabus, but I can send everything. Basically, there are Dubrovin's notes, and it should be more or less enough. There are also some other books like Courant and Hilbert, Tikhonov Samarsky, someone else. I can also send them. And there will be also last year's problems, and probably I'll add some problems this time also of the similar form. Okay, so are there any other questions? Okay, so thanks for your attention.